morning, everybody. Welcome back to Galois Theory. How are you all doing today?
We're doing okay.
Do y'all know that including today we have 4 classes left? Calm yourself. All right. No. There are classes going on elsewhere in this building. Yeah, Tuesday, Thursday next week, and then the following Tuesday is the last day.
I'm not ready to graduate.
So with that in mind, I changed. With that in mind, I decided to change plans a little bit for today. Originally, I was going to do today, we were going to go over like the more general fundamental theorem of Galois theory. But I decided we're going to leave that for the finale now. Instead, what I want to do is solving the quintic with radicals. Why you can't necessarily do that, but you can with degree up through 4. So plan for today. We're going to take a break and not do anything with field extensions today. We're going to do some good old-fashioned group theory.
Oh.
Talk about solvable groups.
We love that.
Did we get a packet?
Oh, yes, there's a packet. Usual office hours next few days. Don't forget you have homework 7 due next Tuesday. Yes, homework 7 will be the final homework of the semester.
Whoa.
But don't worry, there'll be a final.
Is it a take-home final?
It's a take-home final.
Are
Partners.
we getting to take-home final before the final?
Yes.
Okay.
Probably sometime next week is the goal. Mid-next week is my goal. You'll all have like a week to work on it. Such. And no in-class final exam. It'll just be a take-home final. Same rules as with the take-home midterm.
On the homework, do we just not use the Galois correspondence for anything? We need to prove the normal subgroup part and prove the normal extension part.
At least explain to me one of those, and then for the other you can just use the Galois correspondence.
Okay.
Yay!
Yay!
We did that.
So, yeah, you can assume the Galois correspondence result from last class. And I mean, said you still need to show one of them.
Yeah, sure.
I don't know what
sure you wanted to specific direction.
I'll just, I mean, the intention is that you prove the normal subgroups and then use that to say something about the normal field extensions. But if you would rather do it the other way around,
The other way.
okay, Miss Contrarian. Do part F before you do part E, fine.
It will be backwards on my homework.
Okay. As long as you do one of them, that's fine. Any other questions or comments before we get started for today? Oh yeah. Why did the ankle have so much trouble taking out a loan? Ankle had such a hard time taking out a loan because his parents refused to co-sign. Haha, trig and taking out loans, everybody's favorite things. And with that,
Oh, ankle. I thought you said ankle.
I did too!
I was like, what does this have to do with feet?
is my accent that bad?
I understood you perfectly. Because they all
Well, what I heard was, why did the ankle drag around the wall?
Alright, Bart, calm down.
Yeah, that's fine.
Alright, so today what we're going to be doing is we're going to be talking about a special type of group that those of you who had me for 410 we did not talk about in the fall, and I'm guessing those of you in the Dr. Hutchinson group probably did not see solvable groups either because they're a little bit complicated. But are going to be very relevant to what we're doing with insolvability of the quintic. Hint, the solvable group has something to do with solvability of certain equations. But before we get into solvable groups, I thought we'd do a brief review of normal subgroups, also because this might be helpful for homework 7. So to start with, I just want to talk briefly about what it means for a subgroup to be normal. Where there's a bunch of different ways that you can say H is a normal subgroup of G. Shorthand notation is H and then the little triangle with the equal sign. That's this for all of you trying to tech these out. H is a normal subgroup of G. Basically, definition is all the left and right cosets are the same.
Why are number 2 and number 3 different?
Well, one is clearly implies the other, but proving that the other implies the first is less easy. So if If number 3 is true, then obviously number 2 has to be true. But knowing number 2 is true, it turns out number 3 would have to be true. But it takes a little bit of work to show that 2 implies 3 here. I will say it revolves around the fact that all cosets are the same size.
That's, yeah, I'm just.
So 1, 2, and 3 are all just kind of saying left and right cosets are equal to each other. Whereas a reminder, when we talk about a left coset like GH, this is not a group or a subgroup. This is just the set of all elements that can be written in the form little g, little h, where little h is anything from the subgroup H, and little g here is fixed. And similarly, big H, little g, is that Mercury? That's Mercury. It's just a set of all elements that form little h times little g.
Never get Mercury by it. It's always HG2, right? So.
Yeah, it's measured in that, but point is, it's whether you take your element G and multiply it by everything H on the right or on the left. And if your subgroup H happens to have all the left and right, if these are always the same set for any little g fixed in your group, then we say it's a normal subgroup. That doesn't necessarily mean that any little g, little h has to be equal to the same little h, little g. That just means that anything of the form little g, little h can be written in the form something else potentially in h times that little g. So, the elements in big H don't have to necessarily commute with g, they just have to pseudo-commute. And then if you swap the order of the g and the h, you might get a different element in h. 4 kind of tells us why, for most of what we've done in abstract algebra with normal subgroups, they're important. It's because normal subgroups are what you need to get quotient groups, where the set of cosets under that operation, h times bh is just combine a and b using whatever your group operation is, h. Those of you who had me for 410, we did an example in the fall where we actually saw where if you tried doing the quotient group structure with a non-normal subgroup, you end up with that operation is not actually poorly defined. And finally, we have this nice result that says a normal subgroup is equivalent to a subgroup that is the kernel of some homomorphism from G to another group.
That's
Say what?
that's fit or close to fit.
We used this to help us prove fit,
Oh,
but it is not itself fit. Strongly related to fit. Hey, no looking fit. So what are some examples? Normal subgroups. AN is a normal subgroup of SN, indeed. That's going to be a very relevant one for today's class. In general, we can even say H is a normal subgroup of G if the index of H and G is 2. Meaning if H makes up exactly half the elements of G, or in the case of infinite groups, if H has exactly 2 left cosets and 2 right cosets in G, turns out that is a sufficient condition for saying H is a normal subgroup of G, which is a generalization of this, since AN is half the elements in SN. Those of you who had me, this was I forget if it was a homework or an exam question, but I made you all prove this at some point.
I think
Was it? Okay.
yeah, you weren't nice enough to
Yeah. What if H is a subgroup of G and G is abelian?
It's just normal.
Yeah, every subgroup of an abelian group is necessarily normal. Why? Because, well, if your group's abelian, then everything commutes with everything else, so obviously these sets are going to be the same. If you're in an abelian group where everything commutes. You don't necessarily have to have an abelian group. These are very much not abelian groups, and yet you can still have one being the normal subgroup of the other. What about this one? SL2R and GL2R. I haven't seen these in a while. Anybody remember what these are? Like it?
SL2R is the set of all 2x2 matrices with determinant 1, is it?
Mhm.
And GL2R is the set of all 2x2 matrices with positive, well, not positive, non-zero determinants.
It's the set of all 2x2 matrices where that are invertible, or in other words, that the determinant is non-zero. What's the group operation here? SL2R is a subgroup of GL2R. Is it under matrix addition or multiplication?
Well, SL2R is under matrix multiplication.
What about GL2R?
I don't. It's also under multiplication. It's
It is.
M is the one that's under addition. Oh.
Yeah. These are not closed under addition. Because you could just take any matrix in one of these, add it to its negative, and boom, you get something outside the group. Or the set.
In fact, it is so not closed under addition that it does not in fact include the identity element of addition.
That is true. Also, it would not have an identity element under addition. But under multiplication, turns out this is a subgroup. This is a normal subgroup. Andrew? Wait.
Yes. Because if we take some matrix T in SL2R and then R in GL2R, or I guess S2, then we want to say that T inverse is in the same coset as S, which
So basically, you want to say if you conjugate a matrix of determinant 1 by a matrix of determinant non-zero, you're still going to get a matrix of determinant 1.
that's not true. Necessarily. Like that
It isn't. If you start with determinant 1,
yes.
I was going to say, because when you conjugate, keep in mind determinant breaks up over products.
Yeah.
So determinant of A and determinant of A inverse would cancel each other out. A little bit easier way maybe to see this is, let's define a map phi from GL2R to the non-zero reals under multiplication.
It's just the determinant.
Phi of matrix A is the determinant of A. What relationship does SL2R have to this map? Parker?
SL2R is the mapping, well, it's always going to be, determinant's always going to be 1. And then, so it's the identity in multiplication.
Yeah, so what specifically is the relationship? We could say that SL2R is the blank of phi. It's the kernel. Yeah, kernel of phi. In other words, the set of elements in GL2R that map to the identity element in R star, which is just the number 1.
Kernel.
I think we remember having to do this in the homework too, I think.
Mhm.
Yeah.
Indeed, we did. Indeed, you did. And hence, since phi is a group homomorphism, just comes from the fact that determinant of A times B is determinant of A times determinant of B. The fact that SL2R is the kernel of some homomorphism from GL2R to another group. Property 5 in this packet is enough to tell us that SL2R does have to be a normal subgroup of GL2R. Any questions or comments related to that? Eleanor?
Didn't we also say a group generated by a single element is a normal subgroup?
Group generated by
No,
a single element.
That's not true. Like, if you mean the whole group is generated by a single element,
Well, then it's just abelian.
yeah, then it's cyclic and it's abelian. But you can have cyclic subgroups that are not normal. Assuming your group is assuming they live inside of a non-abelian larger group. That might be relevant for homework 7. So what would be a counterexample? Some subgroup that's not normal. the
I'm
rest.
not at all sure about this because I'm making it up, but how about GL2R under all matrices and matrix addition?
GL2R is not a subgroup of all matrices under matrix addition.
That's where I was being stupid. I knew I was being stupid somewhere.
As a subgroup of, say, S4, like just the elements that permute like 1 and 2.
Elements that permute one. So just like
It would be S marked to S2. Like,
copy of S2 inside of S4. Yep, that would certainly be one. Here's one I had in mind. Let's go back to D4, since we were talking about that one on Friday. Now I'm going to take subgroup generated by S, a single reflection of the square. Oh, hey, look, it's a cyclic subgroup. So this, as a subgroup, as a set, consists of S and the identity element. So tell me, if we were to take everything in this subgroup and multiply on the left by S, what would we get?
The left by R, do you mean?
On the left by R. I didn't say that, did I?
You said on the left by S.
On the left by R, yes.
RS and R.
Yeah, we're going to get RS, R times S, and R times E, which simplifies down to just RS and R. If we do the same thing on the right, though, well, we'll get SR and ER. ER.
Which is R.
That's R squared.
S.
R cubed or.
R cubed S,
Oh, yeah,
since we're in D4.
I
If it was D3, it'd be R squared
Oh,
S.
yeah, that's why I got mixed up.
And these end up not being equal, and this ends up being a non-normal subgroup. Because we can find a left and right coset corresponding to the same element, R, that are not equal to each other.
But the group generated by R has a good chance of working.
Group generated by R will have index 2. It's half the elements in D4, and thus will be
Oh, yeah.
by this result.
Does D4 has normal subgroups, so it has to.
Oh, sure.
Yeah.
Here's
Generated by
every group has normal
Oh, yeah, the
subgroups.
identity and then the group itself or something.
Yeah.
And those are-
D4 is a non-trivial one. Take any subgroup of index 2, you'll always get there.
Wait, R itself?
Yeah, subgroup generated by R. Subgroup generated by R squared, because R squared is in the center.
R
Subgroup generated by R cubed is the same as subgroup generated by R, so yeah,
I
that would work.
figured, yeah.
But subgroup generated by S is no good in this case.
R squared doesn't have index 2 though.
No.
It just works.
No, for that one you need a different argument, but you could use that R squared is in the center of D4, meaning it commutes with everything in D4, and thus R squared will necessarily give you the same left and right cosets.
I forgot about center and center.
I know, all these fun 410 topics coming back to haunt you.
Oh yeah, that's
Any questions or comments relating to normal subgroups? I went through all that really quickly, I realize that, but I kind of expect that you've seen that in, you've seen this in Math 410 before. All right. What do you do when you don't want to get fit?
You get
You
back.
sit.
You get
You sit! You've all seen the first isomorphism theorem, but I'm guessing most of you at least have not seen the second.
We talked about the third though.
We've seen the first, yeah, those of you and me, you've used the first quite a bit. We talked about the third and the fourth. It's finally time to unveil the second isomorphism theorem.
If the first is fit and the second is fit, what's the third one?
I think we were very deliberately not saying that part.
I just wanted to
Not
be
falling for you.
I just wanted to be that guy. It could be
Same reason I call it gag, even though there's only one G in the version that we talked about. All right, so here's second isomorphism theorem. Sit.
I'm doing it.
We're gonna let G be group. In a normal subgroup of G, and H is some subgroup of G. H may or may not itself be normal.
Okay.
Well, then we can say several things, turns out. First thing we can say is that N intersect H is a normal subgroup of H. We can also say that N is a normal subgroup of NH. And finally, we can say that H quotiented out by N intersect H is going to be isomorphic to NH. Mod N.
That is.
What is NH?
Good question. What is NH? I don't know. What would you guess this is?
Multiply all the elements in N by
All the elements in H.
which N is
Sort of like
H.
super cosets.
Okay.
Wow, idiot.
Now, turns out this gives us a subgroup of G. The fact that this forms a subgroup relies on the fact that N is normal. If N was not normal, this would not give us a subgroup.
So basically for NH, you just kind of create a giant like Cayley table, and then like all the answers of the Cayley table are just going to be your next step.
Yeah, where you're restricting yourself to the portion of the Cayley table where you have things in N on your rows and things in H in your columns.
That's pretty egregious.
It is. Turns out, I don't feel like reading this, but turns out I should give you this one fine. Turns out,
Yes,
No, you don't.
please do that.
oh come on.
Why?
It would be so fun.
I have to work with you.
Well, that's a good thing. I would do it.
Eleanor, you do not have to work with him if you don't want to.
No, it's fun.
It's not that hard. Alright, let's take a look at this. What's going on here? Alright, so first things first, let's prove parts 1 and 2, which are pretty quick. So proof part 1, we're just going to show that if you conjugate some element in here by some element in here, you get something back in here. So for part 1, we're going to let X be an element in the intersection of N and H, and little h be an element in big H. And I'm going to look at the elements H, X, H inverse. Where does this thing live? Well, first of all, I claim this lives in H. Why is that?
Because all
Yeah. That's just, since literally little h, little x, and little h inverse are all elements in H. So by closure of big H as a subgroup, HX, H inverse has to be in H. I'm also going to make an additional claim. I also claim this lives in N.
Ah,
Oh.
Oh, because it's.
Any rest?
what she said, because all of them
Well,
are
where's
in,
folks?
no, because they're all elements of G and N is a normal subgroup. So since X lives in N, and the H's live in G, therefore H, X, H inverse must also live in N.
Yep. So yeah, exactly. If you conjugate something in N by something in G, meaning you take something in N, multiply it on the left by some element in G, and on the right by the inverse of the same thing, you're necessarily going to end up back in N because that's kind of one of the definitions of normal subgroup. Specifically, number 2 from the front page, or 3. All right, well, HX, H inverse is in H. It's also an element in N. So what can we conclude about it?
It's in a lot of stuff.
Where else does it have to live if it's in both those things, Seamus?
The intersect.
The intersection. Oh, there's our proof of part 1.
Whoa.
And it's N intersect H is a normal subgroup of H. Because if you take something in N intersect H and you conjugate it by something in H, you end up back inside N intersect H.
This proof also works to show that N intersect H is a normal subgroup of G, isn't it?
No, because then this step would fail.
But if I just picked an element in G, or no, okay.
Yes, normal subgroup of G because, and are you saying like N intersect G is a normal subgroup of G?
Well, it has to be because N is a subgroup of normal.
Because that's just N.
Yeah.
But if you're keeping this H around, then you don't necessarily know G X G inverse lies in H specifically.
Yeah.
Okay, second part, second part's just kind of immediate. We can just say since N is a normal subgroup of G, G X G inverse is an element of N for any G an element of G, X an element of N. Thus, AX, A inverse is an element in N for any A an element of regrouping NH. And because this is just a more specific version of that. Hence, N is a normal subgroup of NH. Questions or comments about that? Isabel, you doing okay? You gave me a scared looking face for a second. Oh, that reminds me. One of your classmates is giving a thesis presentation 4 to 5 today, which if you're on the Math News list, 4 to 5 today in here. Catherine Harvey will be presenting her thesis, and also Isabel. You should all try and come by, support your classmate.
I am unfortunately otherwise occupied at that hour. Unless I would be here, and good luck, you'll do great.
Thank you.
That's what she says. Any questions or comments about either of these parts before we move on to this isomorphism? So, this is kind of the bulk of the second isomorphism theorem right there. Any guesses as to what we're going to use to prove the second isomorphism theorem?
Oh boy.
The first isomorphism theorem?
We're going to use fit to prove sit. Yep. Yeah. The reason why first isomorphism theorem is a lot more important than the others, I would say, is because the second, third, and fourth isomorphism theorems are all just kind of specific subcases of the first.
Are basically corollaries.
Or basically corollaries, yes. So let's take a look-see. So we're going to define a map phi that's going to go from H to NH mod N, phi of little h. Just give me, you map little h to its corresponding coset. All right. Let's see who remembers their first isomorphism theorem. What do we need to show about phi in order to be able to use fit to get what we want? Lincoln?
We need to show that,
There's kind of 3 things we need here. Give me one of them.
okay, the kernel of phi is M.
Yep. What is what now?
It's M, right?
Because that's the thing we're quotienting out by. We want to say H mod kernel is isomorphic to N.
Sorry, that is not Greek.
Keep in mind, not all elements in N would necessarily work because we need elements in H too in order to just be in the domain of this function. Andrew, what else?
Needs to be homomorphism.
We need that phi is a homomorphism. What's the last thing we need? Parker?
It needs to be onto.
We need that phi is onto. All right.
Is equal to H1.
Sure, or that. So we need to do all of these. Jackson, which one would you like to do first?
Let's do the onto first.
Ooh, onto. Okay, start from the third one. I like it. So in order to show it's onto, we need to take an arbitrary element here and show that it gets mapped to by something up over here. So what does an arbitrary element here look like?
really wanted to just look like H, but I don't think that's true.
Oh, wouldn't that be nice? No, I think it's gonna have to look something like this.
Oh,
For some element n in big N, little h in big H. Because this needs to be in big NH, and this needs in, since we're modding out by n, we need the coset in here. And we need to find something in big H that maps to this. Oh boy.
oh man.
One thing I will mention here is that if n was not a normal subgroup, this would fall apart very quickly. So what can we say about little n, little h?
Well, isn't it, it has to be in the coset H, capital N. Because, or, yeah,
Is it? Because the left and right
Normal
cosets are
subgroup,
equal.
yeah.
And since the left and right cosets are V equal, are V equal, that is the sentence. That means that we can write little n little h as being equal to the same little h n prime for some element n prime, an element in big N. Well, then if we take little n, little h big N, that's going to be the same as little h, little n prime big N. And how can we, what can we do with this expression?
Since n prime is an element in n, then that's the same as h big N.
Yep. Yeah, since this is an element in big N, multiplying things in big N by n prime is still just going to give you a big N. So the little n prime can get folded into the big N. So we end up with just little h big N. Which is phi of what, Eleanor?
H.
Just phi of h. Yep. So that proves phi is onto, because any arbitrary element in the codomain has to get mapped to by some element from our domain. Pete, decide. Which one are we doing next? Homomorphism or kernel?
Let's do
Okay. Is everyone okay with our proof of onto? Yes. Yeah. This is very much relying on, this property right here comes from the fact that n is a normal subgroup of G. So if we didn't know that, then we'd be stuck there. Via homomorphism. For H1, H2 elements in big H, if we were to take phi of H1, H2, well, that's by definition H1, H2, big N. What can we do with that? Isaac?
I want, take out parentheses and then flip H2 around N. I don't know if that actually helps this at all, but I
Oh, you just want to do some normal subgroup messing around with left and right cosets?
Yeah.
I don't think we need to do that. Eleanor?
Well, by property 4 on the first page, NH mod N is well defined, so it's the same as H1N times H2.
Yeah, that's just literally H1n times H2n. What this is defined to be in the quotient. And so I think we can skip having to play around with left and right cosets and just skip straight to this, because what is this? It's phi of H1, phi of H2. So we get a homomorphism.
That's just
Hmm?
Is multiplying anything in N by itself gets you something in N?
Yeah.
So,
Yeah, it comes down to that. And that's true for any subgroup.
yeah.
Wow.
Are you trying to get us the flu with, your H1Ns?
Hey, I'm giving you H1Ns, not H1N1s. Alright, and finally kernel. So what's in the kernel? Well, the kernel of phi is by definition the set of all elements in the domain such that phi of h is equal to, what's the identity element of nh mod n? In other words, what coset of n in this quotient group is the identity element, so to speak? Andrew?
N.
Literally just big N. No, that's the set of all elements little h and big H, such that h big N is equal to big N. Which is, if little h times big N is equal to big N, what's another way of saying that? Seamus?
H is in big N.
H is in big N. And Matthew, what can we say about the set of all elements in H that are also elements in N?
They're a subset.
Well, not necessarily. This doesn't necessarily imply either is a subset of each other. But how can we write the set out without using the set builder notation?
Could you just do would it be that h times n is just an n then at that point? We write out like that.
Probably not phrasing my question well. Parker?
It's in the union.
No, it isn't.
Well,
No,
it is,
Parker.
but that's not what I'm looking for.
Intersection, not
Intersection.
union.
Yeah, sorry, man. This is what I was looking for. Basically, this is precisely the set of things that are in both H and N. So we get H and N. Which, what do you know, is what we wanted it to be. All right. Well, we've proven these three things.
Proven.
We've proven it.
That accent's really hit.
We're proving it now. So now we can use our fit. And then say by fit, H mod kernel phi is isomorphic to image of phi. So that, in other words, H mod n intersect H has to be isomorphic to H mod n. Because we've proven that the image is all of this nh mod n. We've proven that our kernel is n intersect h. And we know phi is a homomorphism, which is a necessary prerequisite to using first isomorphism theorem. And now that we have all that, we are good to go. Questions, comments, concerns? Looking at Andrew, both looking at this very intensely. It seems to be. All right, this might be useful for us here in a little bit. Second isomorphism theorem. But yeah, turns out second isomorphism theorem is really just this particular case of applying the first isomorphism theorem in a specific circumstance, let's say. All right, ready for solvable groups?
I think there's a typo.
There probably is. What is it?
It says m greater than 0, but it only goes up to n.
Oh,
Uh-oh.
bollocks.
Do you want us to use m or n?
It's well,
Which one is in your notes for the rest of this?
well, my notes are the same as yours for what is typed out.
Yeah, but I meant for the what you wrote down.
I don't know. I just have specific values plugged in for the rest of this.
So it's
I'm putting it in.
I'm using n.
Let's use n. I was gonna say I don't think anywhere I rely on it being one or the other. And so
We've gotten in trouble before for making you change variable names. That's why I wanted to know.
true, but we're not ready. Well,
We got straight.
we'll come to the proof here in a couple minutes. Okay, that's a minor enough change that I can rectify. So, who's ready for towers?
I love towers.
Towers of subgroups.
What?
Subgroups living inside of subgroups, living inside of subgroups, living inside of subgroups, living inside ... living inside the whole thing.
You said ... instead of ...
You didn't say maybe that's
I'm sorry, do you want me to change that notation to
Yeah, what happened to it?
bit.
G
That's not all.
is called solvable if for some n greater than or equal to 0.
Wait, it can be equal to 0? Oh, because
Yeah,
it's
that's
hard to
well, yeah,
count.
trivial group.
Okay, yeah.
There exists a finite sequence of subgroups. Starting with the identity, starting with the trivial one as your G naught, which is a subgroup of G1, which is a subgroup of G2, which is a subgroup of G sub n, which gives you the entire group. So basically, it's a sequence of subgroups that keeps getting bigger and bigger and bigger each time.
This
With-
feels like the nested interval property.
I
This
think it's
feels
related.
very familiar to me.
But two things have to happen. Each G sub I has to be a normal subgroup of the one that comes after it. And two, each G sub I plus 1 mod G sub I is abelian. Now,
Which the second implies the first.
well, in order for this to be defined, the first has to be true.
Yeah.
Now, I'm going to make a note. If you look in the textbook, it has cyclic here instead of abelian, which is a stronger condition that the quotient groups need to have. Turns out they're equivalent, meaning if you can do this so that each subsequent quotient is abelian, you can do it where each subsequent quotient is also cyclic. And in math, it's kind of goes back and forth between which should be the definition that's taught. It ends up not mattering. And the reason is because, and the short reason as to why it is because of good old gag, which says that any finite abelian group can be decomposed as a direct product of cyclic groups anyways. So that kind of comes into play here. So if you want, you could replace abelian here with cyclic. And turns out, I tried to do it the book's way. The book left out a couple of major details and the next proof we're going to do with cyclic, and it turns out it's a lot easier to do if your definition just says abelian. So we're going with abelian for now. But note that you could make these, force these to be cyclic if you wanted to. All right, so solvable groups. Holy moly.
I can't believe we can resolve them in water.
Solvable. Actually, if you look in the book, here's another change I made from the book. The book called them The book calls them soluble,
No, that's not it.
There you go.
which is a thing, but it's much less common than solvable groups. And since solvable groups are going to somehow correspond to solving equations using radicals and not solving equations using radicals, I'm going to go with the more common solvable groups.
Yeah.
I just bring this up
Same
because
letter.
I bring this up because if you're following along in the book and you see soluble groups, it's the same thing as solvable.
That's kind of cool.
So here's an example of a solvable group. S3.
Oh, nice.
Sweet. I remember learning that in chemistry.
Yeah, that's nice and soluble, huh? So you know what? So it turns out we can get this with just 3 of these G's. G naught, a G1, and a G2. Here's G naught for you. G naught's always the same, it's a trivial subgroup. Your G sub n, or G sub the last one in your tower, it's always going to be the whole thing. So here's my question. What would be a G1 that we could put in the middle here? Not asking you, because I know you.
A3.
It turns out works nicely. Which, if you recall, is just the set of all even permutations. What does it mean for a permutation to be even?
It has an even number of permutes. I don't know what did we call it. What did we call it?
You're very good. It does involve an even number of something.
I don't know what
Yes.
It is when it can be broken up into an even number of 2 cycles. Yes?
Even number of 2 cycles.
Yeah, that's what I said.
Which in this
That's
case,
not what you said.
which in this case is just the identity element
The 3 cycles,
and the 3 cycles.
because each 3 cycle is actually 2 cycles inside a trench coat.
Sure.
You-
That's one way to describe it.
Having fought three syllables in a trench
That's a new joke for your story.
Alright. Alright, someone explain to me, why is G not a normal subgroup of G1?
Because it's identity, and then if you multiply it by anything in any way, it stays the same.
Oh, hey, because the
It
trivial
also
subgroup.
happens to be an element of A3.
That is important.
Well, yeah, I mean, G naught needs to be a subgroup of G1.
Otherwise, we'll
Because the centralizer
Yeah, well, I'll just say because trivial subgroup is always a normal subgroup of whatever you're looking at. What do we get if we take G1 mod G naught?
You just get it back.
We get, well, it's isomorphic to just G1.
Right.
And is that an abelian group?
Yes.
Hint, it has 3 elements. What's the only group of order 3?
Abelian one.
It has to be isomorphic to Z mod 3. If you have a group with a prime number of elements, it's always going to be cyclic and hence abelian.
What's that?
What a face.
Guys, calm down. Alright. Yes, Parker.
I was gonna answer that you just wrote there.
Okay, answer me why. Why do we know that G1 is a normal subgroup of G2?
It is, you do the index, then you get 2 with S3.
Since, yeah, G1 and G2 has an index of 2.
The size.
Which means, and anytime you have a subgroup that's half of the group, that's automatically going to be a normal subgroup. And what do we get if we take G2 mod G1? What's that isomorphic to?
Z mod 2.
It only has 2 elements, since the order of this has to be order of G2 divided by order of G1. Lagrange's theorem, anyone?
Oh.
Number of elements in the quotient group is equal to number of elements in here divided by number of elements here.
Oh,
So there's 2 elements, which means it has to be isomorphic to Z mod 2, which means it's
Why is there only 2 elements in that?
because if you want to count the number of cosets, number of elements in a quotient group, assuming everything is finite, Lagrange's theorem, which I'm guessing you probably saw with Dr. Hutchinson, if not, I need to have a conversation with that man, is equal to this divided by that.
The only thing is, I think that why would, for some reason, I don't know if I'm just lost what S3 is, but like, wouldn't there also be 2, 3 as like one of the elements in it?
In S3, yes, but in G2, but not in G1.
Yeah, so when you divide, wouldn't there be
What
3
are the
elements
elements
left, so
of
wouldn't it be
Because it's
Well,
cosets, so they're all
all
grouped together.
cosets?
Yeah.
Yeah, there's 6 elements in G2. These 3 and the 3 individual 2 cycles, 1, 2, 1, 3, 2, 3. Let's write this out. So here's all the permutations in S3, right?
Yep.
So 6 of them are in G2.
Mhm.
Only 3 of those are in G1.
Yeah.
And so Lagrange's theorem says to find the size of the quotient group, you can just take order of number of elements in this group divided by number of elements in that group. It just comes out to this.
I was just Neanderthalically like subtracting it.
Oh, 6 minus 3 is not
But I
2, but it's also not the same as division. So.
Is the other coset in that, isn't that just gonna be one of the 2 cycles?
Yeah, well basically if you wanted to look at cosets, if you want to look at elements of G2, G1, here they are. Yeah, no, G1. And pick any 2 cosets. Pick any 2 cycles. What's your favorite 2 cycles?
Alpha 1,
here are the two elements in G2 mod G1. There's two of them, hence order of the quotient group comes out to 2. Like, is that a hand or is that just a innocent sign?
So S sub n is always solvable because you can always create this sequence with just the trivial subgroup and then A sub n and then S sub n. Right?
But they're not always isomorphic to.
Well, I don't know, because keep in mind, this is not always abelian in this case. A sub 3 happens to be abelian. A sub 4 no, not. So how about we take a look at S sub 4?
That could possibly relate.
I wonder if this one might work, but S sub 5 just might not.
Yeah.
I
There
wonder.
would be no reason for that to happen.
Wait a minute. Weird. This can't be related.
So let's do S4. Turns out we can get there with G0, a G1, a G2, and a G3.
Is there?
So why do we need the G3 also? Because
Because that's the whole thing.
You gotta be.
nobody could
Why do
we
we
just do G0, G1, and G2 and have G2 be the whole thing? Why do we need the 2
Because-
intermediate?
Can you find a way to do it with only one intermediate?
And it has to be a
It has to be
So
So
completely.
that's
Okay.
the abelian.
If you can find a way to do it with only one thing in the middle, then Emily Rose would be my guess.
I'm going to assume the answer is no, but
I believe the answer is no. I'm not 100. I'm pretty sure the answer is no.
But G2 can still be a.
Well, if you can find a G2 and G1, then it's gotta be. Right?
All right. Anybody want to propose a subgroup for either G1 or G2? Isaac?
G2 should be A4.
G2 is in fact A4. G1's a little bit trickier because there's not like a nice, easy way to describe this.
Can't we just write it
What
as
if-
the elements of one to be in there?
Oh, that's what we're going to do. What elements do you want to be in there?
That's an excellent question.
It turns out it's going to be the set of all products of disjoint 2 cycles. So G1's going to have like the 2 cycle 1, 2 times 3, 4, 1, 3 times 2, 4, and 1, 4 times 2, 3.
Does that not have like a fancy like shorthand name?
I don't know. Hey, Lincoln, does that have a nice, short, fancy name?
Climb for group. Or it's isomorphic.
Oh, it's isomorphic to something with a nice
Oh, it's
name.
isomorphic to the climb.
So let's take a look at each of these. If we were to take, we know G1 is a normal subgroup of G1. G0 is a normal subgroup of G1 because trivial subgroup's always a normal subgroup. And if we wanted to take G1 mod G0, well, there's only 2 groups of order 4. Well, first of all, we can say that's isomorphic to G1. There's only 2 groups of order 4, so it's either Z mod 4 or Z mod 2 times Z plus Z mod 2. It's not Z mod 4 because this is not a cyclic group. Take any of these, each of these is an element of order 2, well, other than that one. So we get Z mod 2 direct product with Z mod 2, which is an abelian.
So if we want to make these cyclic, we have to use something different.
True. There is a way of doing this that doesn't involve cyclic groups, but it's a little bit messier. So I want to just do it this way. Yeah. If you specifically wanted cyclic quotients, then this would not work because this is abelian but not cyclic. But there is a way to do it cyclic with the same number of G sub I. All right. G sub 1 turns out to be a normal subgroup of G sub 2. This one is much less obvious, so I'm just going to leave this one as a.
why isn't G sub 0 a normal subgroup of G sub 2?
It is,
So then why do we need G sub 1?
because
Because we need G sub 2, or G sub 1 mod G sub 2.
because we want each one to be a normal subgroup of the one that comes directly after it. That's part of our definition.
Is G sub
It's condition 1 as well.
It's true that G naught is a normal subgroup of all of these. But the one we want in order to satisfy the definition specifically is that it's a normal subgroup of the one below it.
Well, yes, but I'm still wondering why we needed G1 to begin with instead of just going G0, A4, S4.
Good question.
A4
G,
mod,
this mod that is not abelian.
it's isomorphic to Z mod.
A3 is abelian, A4 is not abelian. That's the main reason why.
Okay.
Okay, so I don't know if this quite gets us there, but an argument for the reason that the quotient group would be abelian is because they're disjoint, so no matter which side you do it on.
Disjoint. G1 and G2?
No, the products are disjoint in G1.
The elements in G1 are
Yeah.
disjoint products, yeah.
So you can reverse them without actually changing what's getting mapped to what.
Yeah.
Alternatively, we could just say that this is 3 is prime, therefore isomorphic to Z mod.
Oh, yeah.
Well, it's not that much.
But yeah, you could do an argument like that as well. Because this is 12, this is 4. Matthew, what's 12 divided by 4?
3.
Very good.
8.
I was going to throw a piece of chalk at you if you said 8, but you said the correct answer first. So G2 mod G1 is isomorphic to Z mod 3, which is so far so good?
Yeah.
And then the last step is kind of the same as it is over there. G2, normal subgroup of G3, just comes from the fact that it's index 2. A sub n is always a normal subgroup of S sub n because it's of index 2. And then, then we just get G3 mod G2 has to be isomorphic to Z mod 2, which is therefore, we get everything we want. S4 is a solvable.
In easy cases, you just start
That's
to
fine.
just break it down by like 2s
Yeah.
and 3s, and then you don't actually have to do any.
Except
It's
that
nice if you can. It's nice when you can. Yes.
But then you can't break it down in 5.
S5 and up are not solvable groups.
Whoa.
Does this have anything to do with, I don't know, degree 2, 3, and 4 polynomials being solvable with radicals, but not degree 5 and up? I mean, maybe that has something to do with, I don't know, the solvability of the corresponding Galois groups of certain people.
Oh.
Oh, we still have 15 minutes.
I don't know.
That's gonna be my, all right, let's end class on that note, but no, we still have time.
I don't know that you haven't shown that degree 1s are solvable. I just don't believe it.
Oh.
Okay.
Oh.
That's crazy.
Oh. Truly, the power is unmatched.
I believe it.
Can we show that you want is a normal subgroup of G2?
Sure we can. I don't want to though, I have better things to do with my time.
Let's keep moving.
I mean you can, it's not that hard,
We gotta
it's
get
just,
to the-
it's just not that
we gotta
interesting
get to the
to do
fun
so,
part.
in my opinion. Alright. Any questions on either of these? I bring up S3 and S4 and Sn as the example because that's gonna be the crucial one for what we need solvability for. On the final, I'll ask a couple more general questions about solvability though. Here's one. Let G be a group, and if G is solvable, every subgroup of G is solvable. And if you have a normal subgroup of a solvable group, the quotient group is solvable. And it turns out for a normal subgroup H, G is solvable if and only if both H and G mod H are solvable. So it turns out we can say, if we know a group is solvable, we can say a lot about the solvability of its subgroups and quotient groups.
B and C seem related.
I mean, they are
They're
related.
kind of saying very similar things,
But backwards.
given
I
that
mean,
you've been only
C is
statements.
really just like a generalization of, well, no. C is a generalization of is B plus other stuff, yes.
Yes.
So let's take a look-see. We're not gonna prove all these, we're just gonna prove the first one, which is the one that's gonna be most useful to us. I think we can try to prove this. So let's prove part A. So let's suppose G is solvable, and we want to show that if H is a subgroup of G, H also has to be solvable.
So,
And we're going to assume it's solvable with a tower. This is called a tower of subgroups, by the way. Yes, I know it's on its side. It's not written vertically. You could write it vertically, and it looks like a tower, but that, I like doing it horizontally because it makes more sense with how we write things out on the board. Okay, moving on. If it's a shut up. Normal subgroup of G1, normal subgroup of G sub n, which happens to be G, with each G sub I plus 1 mod G sub I abelian. And our goal is to show that if we suppose that H is a hold on, I just noticed something.
Oh, no.
No, I think we can just do it this way. Let H be a subgroup of G. And for each I, we're going to let H sub I be equal to H intersect G sub I. H intersects something normal. I wonder if some things we did earlier in class are going to come into play.
Oh, that's kind of crazy.
Well, let's take a look. First of all, I claim that for each I, we can write H sub I as H intersect G sub I. I'm going to choose to rewrite this as H intersect G sub I plus 1 intersect G sub I.
which is still just G sub I because G sub I is a subset of G sub I plus 1.
Yeah,
but-
which is just, this is all just G sub I since this is a subset of that. Taking the intersection just gives you G sub I. But I'm going to move some parentheses around. And what's H intersect G sub I plus 1? It's H sub I plus 1. Questions or comments thus far? So we're just kind of cheekily rearranging the H sub I terms in a way that's going to be useful for us in just a second. Because what are we going to do next? We're going to take H sub I plus 1 mod H sub I. Which, by what we just did, is H sub I plus 1 mod H sub I plus 1 intersect G sub I, which is isomorphic via sit to what, Isaac?
H sub I plus 1. H sub, wait, and then,
Times G sub I,
yeah.
Mod.
Group, H sub I plus 1. Wait, oh, did I? Yeah. Okay,
I think, right?
makes sense.
Yeah, in the end, yeah, the normal one, the G sub I. And that, what do we know about this thing? second one, we know h sub I plus 1 g sub I is going to be a subgroup of g sub I plus 1. Why is that?
Because we're taking a product of two things. One of them is in G sub I, which is in G sub I plus 1. And one of them is H I sub I plus 1, which is also in G I plus 1,
Wait.
by how we define H I.
Yeah, h sub I plus 1 is just h intersect g sub I plus 1. So this has to be a subset of g plus sub I plus 1. This kind of by definition is a subset of g sub I plus 1. So if we multiply things together, the fact that use the closure of g sub I plus 1 to get that that's a subgroup of g sub I plus 1. So this whole thing is going to be a subgroup of g sub I plus 1 over g sub I. What do we know about g sub I plus 1 mod g sub I? Yeah. And since g sub I plus 1 mod g sub I is abelian, what do we know about all the subgroups of g sub I plus 1 mod g sub I? So what do we know about isomorphic copies of subgroups of g sub I plus 1 mod g sub I? And h sub I plus 1 mod h sub I is isomorphic to a subgroup of this thing. H sub I plus 1 mod h sub I is abelian. Sound good? I'll give you, let's see, Emily Rose, I'll give you one guess as to how we're going to make a tower of subgroups leading up to H that makes H solvable.
I wonder if it's not the identity, and then H intersect G1, H intersect G2, and so on.
I mean, I'm just going to call them H sub I's, but yeah.
Well, I thought you wanted what the H sub I's were.
Oh yeah, oh well, I just wanted what the tower is.
Yes, the tower of the HIs.
So we can conclude then that if we take identity element, which is H naught, which is a normal subgroup of H1, is a normal subgroup of is a normal subgroup of H sub n equals H is a tower of subgroups making H a solvable. Any questions, comments, concerns? Yeah, fun use of second isomorphism theorem to kind of take this weird thing and make it isomorphic to a subgroup of something we already know from the something we can analyze from the solvability of G. I should say since each of these is abelian. So for each H sub I plus 1 over mod H sub I is abelian. So on and so forth. We're not going to prove parts B and C, they're in the book. Part A is the one that's going to be the most useful to us though. So, for our next trick, we're going to show that S sub n is not a solvable group. Hint, if Sn was solvable, all of its subgroups would have to be solvable.
Everything is solvable.
True,
Everything finite,
true,
which is
because
still.
Cayley's theorem, every finite group is isomorphic to a subgroup of a symmetric group. Can you think, but let's say S5 in particular. Isaac, would you care to guess a subgroup of S5 that we can show is not solvable?
We're in A5.
How about something with no normal subgroups at all? No non-trivial proper normal subgroups at all? A5.
Yeah. Wait, oh,
Yeah, no, you're right. I'm just being dramatic and doing a poor job of it.
so we can show that A5 has no.
Yeah.
Okay.
Turns out A5 has no normal subgroups whatsoever other than itself and the trivial one, which in turn means that A5 can very quickly be shown to be not solvable. And since A5 is not solvable and it's a subgroup of S5, that means S5 must also be non-solvable. Insolvable. Insoluble. I don't know why the book
Does not
uses
dissolve in math.
I don't know why the book does it that way. It says soluble instead of solvable. It's very. I've seen it before, but like it's very weird.
Parentheses.
It dissolves
Just
into the
just
numbers
solve it into math.
Looks pretty.
I mean, solvable comes from solving equations, but whatever. All right, that's enough for today. Call it there. So when we come back next time, we'll finish proving S5 is not a solvable group, and then talk about what does that have to do with Galois groups and field extensions, and ultimately, what does that have to do with solving quadratic equations? You all have a good one, and I will see you all on Tuesday.
Homework.
Yes, bring homework.
Unless your favorite subject.
Thanks. Bring homework. Yeah, bye later.